Thank you, sir. Moving on to the first session. The theme for the first session is Ancient India's Contribution and Achievements in the Field of Science. The moderator for the first session is Professor C.K. Raju. Professor Raju is MSc in Mathematics from Mumbai University and PhD from Indian Statistical Institute, Kolkata. He initially taught and researched in formal mathematics and quantum field theory. Later, he joined CDAC to play a key role in building India's first supercomputer, Param. He is an honorary professor at Indian Institute of Education, emeritus professor at SGT University, Gurgaon, and a Tagore Fellow at the Indian Institute of Advanced Studies, Shimla. He was a fellow at IIAS and on the editorial board of the Journal of Indian Council of Philosophical Research. A prolific thinker and an academician, Professor Raju has authored several books which include Cultural Foundation of Mathematics, where he proposed a new philosophy of maths called zeroism. He is a widely traveled scholar and has delivered lectures across continents. He has received numerous awards, which include TGA Award in Hungary in 2010 for correcting Einstein's mistake, and is also the recipient of Bharati Dharohar Award. I now hand over the control to Professor Raju. Over to you, sir. You may kindly share your presentation and unmute yourself, please. We can see your content, sir.
You can see? Well, I can't see. I don't know what. Finally, yeah, I can see. Okay. So thank you very much. Thanks to the Army War College for making taking, I should say, a revolutionary step. But of course, I'll try to keep to my time. We need to understand that punctuality is not the best sort of thing in intellectual discourse, where it is important that things should finish rather than that they should be done in time. Anyway, so I'm going to speak about ancient Indian mathematics. And I want to start with some simple clarification. When we talk of Aryabhatta, it is not Aryabhatta. No, why not? Because Bhatta is something different. Bhatta is Brahmin and Bhatta is Dalit. I have an article on this in Jansatta. Maybe you can take a look at it. But I won't have time to go into all that. So let me just explain that. The wrong spelling destroys the story of ancient India's integration across region and caste, because the disciples of Aryabhatta from Patna were the highest caste Nambudri Brahmins from Kerala. And there's a recent article on that. You could take a look at that. Then there is this issue of Vedic math. The approach paper mentioned something about Vedic math, and my assertion is that there is nothing Vedic in Vedic maths. This is an article that I wrote for the Hindu long back. So you can take a look at that again. The links are there. They can be shared. Similar thing in Jansatta. The point is, Vedic math has no connection whatsoever to the Ved. Bharati Krishna Tirth did not give any source when he was challenged. And the book itself says that obviously these are not to be found in the Atharva Ved. And why Atharva Ved? It should be Yajur Ved and so on. But anyway, the actual math found in the Ved is different. It is detailed in a book by M.D. Pandit, very little known book. So the point is that the title of Vedic math is grossly misleading. And the Ved is sacred. So to use it for misleading marketing is wrong. It's not even ancient. So there's a big discussion with some of the promoters. It is there on my website. Again, I won't go into this link in too much detail, but there's a huge discussion that has taken place. And the point is that they say it is ancient. And they say it is not Vedic. We agree. It is not actually in the Ved, but this should be put on the cover. But how do you know it is ancient knowledge? You see, it's probably modern. Just now, Professor Mishra mentioned the Katapayadi system. So, you see, the point is nothing about not a single ancient source mentions Vedic mathematics across 3,000 years. No traditional Indian mathematician. And the Katapayadi system, which is of recent origin, is there. I mean, not so recent. It may be about 1,000 years old, but it is certainly not of Vedic times. So it's probably modern. And the other issue is that everything ancient is not Vedic. There were lots of people who were opposed to the Veda, the Lokaya, the Buddhists, the Jains. So, they say that, you see the kind of thing they say about the Veda, that they have the three faults of untruth and self-contradiction, that is Vyaghat, and tautology of Punurukti. And they are only the incoherent rhapsodies of names. Now, this is there in the Sarvadarshan Sangrah, just translated long back, of the Lokaya. So the point is, if it is just because something is ancient, it does not become Vedic. Even if it is ancient, it is not. And it has no relevance to science and technology. So if you remove the misleading marketing label Vedic, then there is nothing left there, just some simple tricks of mental arithmetic, which are of no value to science and technology, especially today. And what does it seek to replace? It seeks to replace genuine Indian arithmetic. So what you study today is not something which came from the West. It came from the West, but it went first from India. So, to summarize, we should not be talking about things like Vedic mathematics, which has nothing to do with Ved, which is just a simple set of tricks, which has no relevance to science and technology, and which eliminates the real Indian contribution. Okay, and makes us a laughing stock. We should not do that. So let me quickly explain how Indian mathematics went to Europe. Went to Europe and came back. And the background is Al-Khwarizmi. He was an Arab, and Indian mathematics first went to Arabs. Al-Khwarizmi, that's where the word algorithm comes from. That was his Latin name. It went in three phases. So the first time it went was, there is a big article on it again. I don't want to quote it. Just want to give you an idea. First was Gerald of Aurilak in the 10th century, who later became Pope Sylvester, who imported it from Cordoba. Then it was Fibonacci, the 12th century, who imported it from Africa and wrote Liber Abaci. And third phase, it was Christoph Clavius, 16th century, who wrote practical arithmetic imported directly from Kochi. Now, the key point I want to tell you, because today's topic is about relevance to modern technology. And in that context, the key topic I want to explain, using the simple example of arithmetic, is that Europeans failed to understand elementary Indian arithmetic of algorithms. And they failed to understand it for 6th century. We are talking about addition, multiplication, division, square roots, etc. They failed to understand. That's a critical issue. Why? Because their native arithmetic, which you call as Roman numerals, was different. They used the abacus. And it's a completely different system. So the first importer, of course, was Gerald of Aurilak. What he did was that he got a special abacus constructed because he had written a book on the abacus. He thought that's the only way to do arithmetic. And so he got a special abacus constructed. This is from 976. These are the first so-called Arabic numerals. Take a look at them. Now, the point that you see, he understood that a blank space represents 0. He understood that point. But he did not understand. What was the critical thing that he did not understand? It's not that he did not understand the decimal system. He understood the decimal system. He understood the place value system. But he did not understand the efficiency. Because he got an abacus constructed, it's a subtle point. The efficiency of Indian arithmetic depends upon the algorithms and not the primitive coin counter system which is used in the abacus, in the Roman arithmetic, the way Romans did it or the way Europeans did it. So this is the point. It is more efficient. It's not about 0. It's not about decimal place value system. It is efficient. So let's take a simple example. If you look at 1788, it is written using 12 symbols. And the largest number somebody mentioned, in Yajurved, it is 10 raised to 12. Yajurved 17.2. Or you find 10 raised to 53 in Lalit Vista Sutta, which is the life of the Buddha. All right, I have the translation here, but I don't know whether you can follow it or I can explain it to you so quickly. But there is a Tallakshan, and that Tallakshan is used. It goes up to 10 raised to the power 23. All right, it's available here, chapter 12. Whereas Romans could only have 10,000 as the largest number. So Roman arithmetic primitive. Now let's take the case of addition. Simple addition sum I want to perform, 89 plus 89. It's a trivial matter. But if you do it with Roman numerals, you write it down like this. And then you expand the x, 1x is to be written in full form as VIIII. All right? Then what happens is that you think of these X, L, V, etc. as counters or coins of 50, 10, 5, and 1. Then you pool all the coins together and you count them, that is, and then you replace them. Okay? So when you do that, what happens is that you simplify. So you count 8 times, there are 8 ones, then simplify it and then replace 5 ones with 1 5 and so on and so forth. You continue in this fashion. So this takes a very long time. Okay, I'll give you the answer because there is no time to really go through it in full detail. It takes 25 operations. 25 operations just to do a simple addition. But now look at multiplication. Let us suppose we want to multiply 89 into 89. And what do you have to do? You have to add 89 to itself 89 times. That was the way Europeans used to do arithmetic. So that 25 operation must be repeated 89 times. You get 2,225 operations. And same way for division. Instead, if you are looking at an algorithm, this is a very simple algorithm which you do. This is an Indian algorithm. All right, from Al-Khwarizmi to Europe and then back to us through colonial education. So it just involves 10 single-digit operations compared to over 2,000 in the Roman case. So this is what I mean by saying Indian arithmetic is very efficient. This is a very important point to understand. People keep talking about zero, they keep talking about this, that. They don't talk about the efficiency of Indian arithmetic because we study our history from Western sources, and Western sources did not tell us that. They threw zero at us, like to throw some little bit to somebody to, to a dog, to a tidbit. So it's extremely inefficient Roman arithmetic. And that is why Europeans themselves adopted it. Because efficient arithmetic gives a comparative advantage in commerce. And the Arabs were better traders, and therefore the Europeans learned from them. Fibonacci learned from them. He was a Florentine merchant, and therefore he brought it back from Africa and wrote a book, Aryabhatta, in the 13th century. All right. So some Florentines accepted the new system, but many were suspicious. What is this newfangled Arabic numerals? The problem was this is where zero comes in. They were suspicious of zero. The Roman numerals are additive. So XII means 10 plus 1 plus 1. But in the place value system, you can't just add the digits. But that is what they were accustomed to. And so the idea was that if you put a zero at the end, you can increase the value of any financial contract by an arbitrary amount. And therefore, Florence passed a law that if you use these newfangled Arabic numerals, write any contract, you must write it also in words. Not enough to write numerals because these numerals are suspicious. That is where the story of zero starts from Florence, because they did not understand, they could not adjust. Now note this cultural difference in ways of doing arithmetic. That is the important thing. That is what caused this lack of understanding and so on. And we still follow that in writing checks, and the very word zero is from cifra, which means cipher, which is a secret code. So that's the origin of zero. But you see, the point is, they told us a story with a grain of truth. Contribution of ancient India to mathematics was zero, but the real aim was to hide the story of the importance of their own arithmetical incompetence. From Greek times, Roman times, they were arithmetically challenged. There is even a film song, Zero Diya Mere Bharat Ne. You know that? I have it here, but I don't think I'll go over it because there is very little time. So, Manoj Kumar in Purab Pashchim. So, India did not teach the world to count. That's not correct. The world knew how to count. But India taught an efficient arithmetic. It wasn't just zero. Okay, so I have a half an hour lecture on that. But please remember that ancient India's contribution was efficient arithmetic. And the story I'm telling you is that The Europeans were arithmetically challenged. They were far behind us. And therefore, Western historians hide that history. We never wrote our own history. We only copy what they say. We never did it. We talk about how great we were, but we are not willing to devote resources to study it. But that is what needs to be done. Can't just talk about it from, from the, let me say, enemy sources. You have to talk about it from your own sources. So why do we erase that real history and keep going back to zero and Vedic math is something problematic. Let's look at fractions. So fractions, Europeans were very bad at fractions. They had no way to represent fractions. How do you write fractions in Roman numerals? You can't do it. They knew only about parts of 12. So that is, they were arithmetically challenged. And you can see that today. You don't need any great sources. It's there in the calendar. Okay. So because they could not count, because they could not get fractions, they had a big problem with the calendar, the Julian Reform, which corrected the calendar after Julius Caesar's conquest of Egypt. With great fanfare, it used a leap year system. 365 and 1/4 day. That is wrong figure, completely wrong figure. And it is known to be wrong from the time of Aryabhatta. But we adopted it, we still adopt it with a system of leap years. Why leap years? Because they could not write fractions. In fact, even that leap year system, the Romans did not understand. And you know why August is called August? Because Augustus Caesar was the first to understand that you should count every 4th year, and they counted starting from the present year as 1. So the 4th year came out to be the 3rd year. So this went on for 20 years. They were that bad at counting. They did not understand the concept of leap year or fraction. So we know that Julius Caesar, July got named after him. It has 31 days. So August was also named after him. And therefore, that makes the whole calendar extremely unscientific. Okay, but we follow it all, need 30 days, 31 days. It's not a scientific method of timekeeping. So this became the Julian calendar was adopted as the official Christian calendar in the 4th century at the Council of Nicaea. And they brought it to us, and this is our official calendar today. Most people only know their date of birth on the colonial Christian calendar. And that is based on the Gregorian Reform. See, the Gregorian Reform was done in the 1582. And this is when fractions were first introduced in the European syllabus by Christoph Clavius, who authored that reform. And he wanted to say that the actual duration of the year is 365.241 tropical days. He couldn't say that. And so he still used the system of leap years. And the disadvantage is, he did it like this, that every 100th year is not a leap year, so you subtract 1. And every 1000th year is a leap year, so you add 1. And therefore you get that figure. But this is right only on a 1000-year average. The Gregorian calendar is still not right, doesn't get equinox right every year from year to year. So this is the disadvantage of bad arithmetic. And it is there right in front of you in your daily usage of the calendar. You should understand it. All right, let me just summarize this quickly. I've taken a lot of time. Efficient Indian arithmetic went to Europe and was repeatedly brought back. It went 3 times, came back. And the real story of zero is that Europeans took 6 centuries to understand Indian arithmetic. It was efficient, went repeatedly, and it took them a long time to understand. All right. Now let me come to the relevance of modern technology. You wonder, what am I talking about? Where is the modern technology here? So let me tell you the modern technology. That's the theme of today's seminar. So what's the implication for modern technology? The thing is, it is relevant. But how do I explain it to you? So technology, first of all, is about people, not machines. See, if you just go buy technology in the market, you want to buy a car, you want to buy a computer or something, then you will say it's a machine and you are paying some money for it. But if you want to build technology, then it is about knowledgeable people. It's not about machines. You have to have people to do it. When I was in CDAC, we built the supercomputer. You understand the importance of people. If one person leaves, then everything crashes. So there have been multiple failures of technology missions in India, including the failure by CDOT. and the failure of the DRDO to build a supercomputer. I won't go into those details. I want to come to the present time. California is the hub of modern technology, the hub of high tech, and especially Silicon Valley. Now, what is this arithmetic got to do with it? I'm explaining. So we think technology is about machines, but they understand that it is about people. Right in the Sputnik crisis, you recall that Soviet Union sent the Sputnik, and that went into space in '58. And the US considered that as a crisis because they said they want to win this technology race. And therefore, they revamped the entire syllabus, especially their mathematics syllabus, so that you are able to teach people how to build rockets to go to the moon. That was their mission. All right. But today, that's not about going to the moon. It's about machine learning, about artificial intelligence, as it is called, and data science. That's the cutting edge of modern technology. Machine learning and data science. So the corresponding math is called 21st century math. And properly trained people are needed. How do you get those properly trained people? The problem is the calculus is very difficult. And so therefore, the California Mathematics Department, Education Department, has proposed a revamped mathematics syllabus. It is here. You can take a look at it. This is the new mathematics framework proposed by California. And now I cannot go into it, of course, it's so many pages. The point is, it is supposed to meet the projected needs of future technology, supposed to prepare people. And what is the change that has been made? You teach statistics and data science. Statistics and data science. And what is the catch? The catch is that this is an alternative to the calculus. All right? It's an alternative to the calculus. Because the calculus is very difficult and people drop it, they said this is the way to have equity. All right? So it has been called canceling the calculus because the calculus is difficult. And now, therefore they say it serves no purpose because you teach calculus in schools and people don't learn anything and they go on and they again take the same calculus course. So this is what the critics have called it, canceling the calculus, and they have asked for it to be revoked. I mean, there are so many petitions and so on in the US. All right, so there is some point in the argument because statistics needs calculus. Now I can't go into this kind of advanced mathematics. What is measure theory, what is average, and what is the Lebesgue integral, and so on. What is probability? Because statistical inference is proverbially misleading. My point is, unless you understand all that mathematics, you can't do statistics properly. It is misleading, and you may make all sorts of errors, or you may want to be misleading. And think of it. Tomorrow there's a machine which will make those decisions. You may write the program today, but tomorrow, you see, it's self-learning. It will grow out of your control, and tomorrow it will be taking decisions. It will say, do this, and it may be just wrong. But you will have no way to correct it. You can't argue with a machine, hey, you are wrong. Better change your decision. So, as you know, there are lies, damn lies in statistics, so there can be wrong results from machine learning. Happens all the time. You see, so many of the programs that are being developed, they get wrong results. So what do? You have to have an understanding of statistics. People who are building the program need to have a proper understanding of statistics and data science. Otherwise, they will arrive at wrong conclusions, they will program the machine wrongly, and so on. So a wrong artificial can be disastrous. All right? When people depend on that decision. So what do you do? So the alternative that I have proposed, and of course there is no time to talk about it here, because alternative is to teach the decolonized calculus. What is the decolonized calculus? Decolonized calculus is the way calculus originated in India as Ganita. How do I talk about it? I have written a 500-page book about it quite some time back. I have also several popular articles and so on and so forth. You can read those. The point is, this is my book, Cultural Foundations of Mathematics. It's a very big, huge book, and it is about the transmission of the calculus from India to Europe in the 16th century. So this is the book. And if you see the subtitle, it's about the transmission of calculus from India to Europe in the 16th century. So calculus originated in India. Not only it originated, it was transmitted. Exactly like arithmetic, it was transmitted. But this happened in the 16th century. Why was it transmitted? It was transmitted because the calculus served to provide accurate trigonometric values which were essential for navigation. So what are the courses? You can take a look, or you can see the video of my MIT lecture, several abstracts. I don't think I have, I mean, here I can just show you what the thing is. Oh, they will show the ad, I'm sorry. So the point is there is a decolonized calculus based on the way calculus developed in India, and there is decolonized statistics, which is based on, if you can see, take a look at my article on probability in ancient India and how it originated in India. There's a talk that I gave in JNU on statistics. Whether we should teach it, it depends upon changing the philosophy of mathematics. Ganit is different from mathematics. And that point is something nobody told you. The way calculus originated in India is completely different from the way it is taught today. Not completely different, significantly different from the way it is taught today. And that is the crux of the matter. That is why it is easy. Exactly like I told you about arithmetic, calculus originated in India, it went to Europe, and it came back through colonial education. But what came back was a less understood form of the calculus, but we accepted it because we think that colonial education is, whatever they tell us is right. So you can take a look at these. These links are there. I have shared the whole thing with the Army War College. You can study it at leisure. I just want to give you a popular level account. It has just come out in this New York-based blog. And here also there'll be ads. Yeah. So this is the first part. The second part is due to come out today. I don't know if it has come out today. No, only part one is there. Second part has not yet come out. So there's a popular level account of these California proposals. And you can see it is to appear today, but US time, so maybe a little later. So you can look under the education sector section of Bology. Now, why didn't I talk about this? I didn't talk about this because my basic thesis is that calculus is difficult because Europeans stole it. But they failed to understand it. I'm talking about Newton and Leibniz, those guys whom you worship as gods. They failed to understand it. Okay, Newton had some silly fluxions and so on and so forth. I've written about it again at great length. But the point is, they failed to understand because they stole. See, when one student cheats in an exam, this is my epistemic test. The person who cheats may copy and write everything, but he doesn't fully understand it. He may understand some part, but not fully. But we blindly imitate that. We are worse. We forget our heritage. And now I'm talking about modern technology. I'm not talking about arithmetic. All right, I'm talking about modern technology because that is where you need calculus and statistics. That is where you need data science. That is where you need machine learning and so on. So that is my epistemic test, that students who cheat in an exam are failed to understand what they do. That is why Europeans took 6 centuries, because their understanding of arithmetic was different. And that is exactly what happened to the calculus. But I cannot explain that point in 30 minutes. Impossible. You don't know calculus. You probably don't know Aryabhatta started it, but you don't understand even the spelling of Aryabhatta. It's very difficult for me. And it is not just enough to tell you what we did. You have to first reject its Western understanding. And that is a very tough job for colonially educated people, because you learn that way. All the people you think are knowledgeable, they learned it that way. And that is what happened. Okay. Yeah, I have given... So that's the solution. So the point is that this is the solution, but I can't talk about it. I'm sorry, we lost 2 minutes in that. Because understanding the calculus is a problem. The colonial mentality is that we just want to imitate the West and copy its mistakes. Now, what I am talking about calculus, I'm talking about 1 + 1 = 2. 1 + 1 = 2 in real numbers, because real numbers are supposed to be necessary for calculus. You need 30 hours to explain that. And all that I will say is, you think that, all right, some mathematician will understand it. Let's take a mathematician from Harvard, from Cambridge, from somewhere. They don't. All right. And even if they do, you want them to discuss it publicly, because their means of livelihood depends upon continuing that formal mathematics. So you should not consult them privately. You need, because Ganit is so different from mathematics. Here's an article in Hindi, which is there. We can take a look between Ganit banam mathematics. Okay. So you need to have public debate. And the prerequisite for that is not that so-and-so got a degree from here, got a degree from there. So many people get degrees from various places. It's my 1 + 1 = 2 test. In JNU, I offered a prize of 10 lakh rupees for anybody who could prove 1 + 1 = 2 in real numbers. So please understand what has been done to your mind. You have been Bantuized. You have been taught that real numbers are essential for calculus, but you don't know 1 + 1 = 2 in real numbers. I can offer that prize again right now. If you can do it by tomorrow, 1 + 1 = 2 in real numbers from first principles and axiomatic proof, without assuming any result from axiomatic set theory, I will give you 10 lakh rupees. All right. And you try and understand, this is Bertrand Russell's 378-page proof of 1 + 1 = 2 in cardinals. Can you understand anything there? This is very easy compared to what I'm asking you to do, which is to do it in real numbers. And so don't judge a person as a math expert just because he has some degree. And NCERT refuses to discuss this. I have a critique. There's a whole video on that. I have talked about it even to the chair of the Parliamentary Committee on Education, and a public discussion on why we should take Ganit. But that is the maximum that I can do. This is not my personal agenda. If you can do it better, do it by all means. And my conclusions then are simply this, that Indian Ganit is very relevant to modern technology, but I can't talk about the whole thing. I gave you just a simple example of Indian arithmetic. So Indian Ganit makes math easy while preserving all practical value. You want to send rockets and so forth, that's the right thing to use. But first we need to understand what real Indian Ganit is and reject these false stories about Vedic math or Aryabhatta, and that requires that we respect our own knowledge, which respect is what Indian society has lost, because colonial education taught us that we are inferior and we must blindly imitate and trust everything Western. So thank you. That's all that I have to say. If there are any questions, I will take them.
Thank you very much, sir. Sir, there is a question from Dr. Ravi Shankar Polishetty, sir. He's online from Hyderabad, sir.
Right.
Professor C.K. Rajuji, wonderful talk. I can't really appreciate enough with my words, but a brilliant talk. Thank you very much for that. Sir, one comment and one question. So the comment is that, in the Bhagavad Gita, Lord Krishna says, Chaturvarna Maya Srishtyam Guna Karmaja Vibhagaha. So you define the caste based on a varna, based on his actions. So when I'm a cardiac surgeon performing treatment, I'm a Brahmin. When I'm protecting my nation, I'm a Kshatriya. When I'm bringing value to the people around me by, bringing our ancient knowledge into practicality, I'm a Vaishya, and as a doctor himself, I'm a skilled labor, so I'm a Shudra. So, sorry, sir, for this comment. Just wanted to pass this comment. And the question is, so I think, with your wonderful analytical skills and being, we should revert possibly on the timings and chronology of the ancient Indian technologies. Just the way you mentioned that this is Vedic, ancient, but might not be Vedic. So maybe shouldn't we consider the recent data coming up from thermoluminescence and other dating technologies of how advanced tools were discovered here in India, which dated back to 1.5 million years? They couldn't have been invented by some nomads or some Homo erectus and other species. So this is my question to you, sir. Shouldn't we be working on the dating again?
I don't think so. Because I think the question is most definitely not of chronology. Everybody is talking about chronology. What we are talking about is epistemology. How was it done, not when it was done. Let us take the case of the Pythagorean theorem, so-called. So Pythagorean theorem, why is it called Pythagorean theorem? Not because you are the first to do it. You say, all right, you have Shulva Sutra, you have Egyptian pyramids, you have so many things before that. But because he did it differently and you teach that kind of mathematics that is there in our 9th standard text. Are you able to hear me?
Yeah, I can, absolutely. Thank you.
Okay, so if you can't correct that, there is no point in saying we did it first. Question is, did you do it better? Or did Pythagoras do it better? So please read my articles and please drop these ideas about chronology. Being first is not important, being better is important. And what we did was better, that is what I'm trying to tell you.
Wonderful.
Chronology is there in my book, but it's not of very great relevance. So especially, let us say, Shulva Sutra, whether it came before Pythagoras, after Pythagoras, not important. What is important is that it did geometry differently with a string, Rajju Ganit. I have a textbook on that. Can we adopt it? It's going to make no difference when it was done. How it was done is important.